Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. And the topic of the lecture is current voltage characteristics of MOSFET. And what we will be learning in this class is basically how do you formulate the current versus voltage characteristics of a MOSFET, metal oxide semiconductor field effect transistor. When I say current versus voltage, I mean to say that if you change the bias on the gate side as well as on the drain side, then how does the current flowing through the MOSFET will depend. That we are supposed to learn in this class. Let us come to the outline of this class or of this particular lecture. We will be looking into the derivation of the IV or the current voltage characteristics, which will give me an idea about on what factors the current flowing in a circuit depends upon. We will be also understanding the transfer curve for various characteristics for various regions of operations. So, I have an IV which is drain current versus drain voltage, and we also have a transfer characteristics which gives you the drain current versus the gate voltage. So, the second one is basically drain current with the gate voltage. We will just in a single slide recapitulate the basic equations which needs to be remembered. We will also learn about the capacitance in MOSFETs, primarily parasitic, junction and voltage dependent capacitance, and brief look at the high frequency CV characteristics and then recapitulate the whole lecture. Let us come to the first one, and that is basically your current voltage characteristics. So, to understand this, the basic framework for deriving any current versus voltage characteristics is to extract the amount of charge which is accumulated near the silicon dioxide interface, right. Once you know the charge, then current is nothing but the charge flowing per unit area per unit time, right. So, if you know how much amount of charge per unit area is available in the inversion region, you could derive the closed form of current versus voltage equations. To do that, we take two basic assumptions, and these assumptions are written here as gradual channel approximation and charge sheet model will be taken into consideration. I will try to explain to you each one of them. Let us first look at the gradual channel approximation. Now, if you look at the MOSFET, let us look at this MOSFET here and I will explain to you. This is the channel length. So, this is y equals to 0 and then this is y equals to L. So, the distance between this point to this point is basically my channel length which I am referring to. Width is in the dimension which is inside the box. Now, if your channel lengths are relatively large, right, then the electric field in the transverse direction, which is, let me assume this to be as the transverse direction, will be much larger as compared to the electric field in this direction, which means that if I say this as Ex and this as Ey, then Ex will be much larger as compared to Ey, right. Why? Because the transverse direction is just the oxide thickness, right, which is of the order of few angstroms, whereas this channel length is of the order of few micron, right. So, it is a 3 order difference in the electric field which you will see in the transverse direction as compared to the longitudinal direction, right. This is what is known as a gradual channel approximation. So, what is a gradual channel approximation? I can safely assume that the variation of the electric field is relatively small in the y direction and it is typically very large on the x direction. So, Ex is orders of magnitude larger than Ey, right. This is known as the gradual channel approximation, and typically this is favored for long channel devices. When you have a very long channel device, right, long channel device will do what? Your dimensions, device dimensions are so large on the length that the electric fields are relatively small. Let us come to the second assumption, and that is known as the charge sheet model. So, we have learned about the GCA or the gradual channel approximation, and we now come to the charge sheet model. So, one more thing which I need to point out for gradual channel approximation is that the rate of change of voltage therefore along y direction, right, with respect to the distance y is much smaller as compared to the rate of change of voltage along x direction with respect to distance x. right? This is relatively large, right? And this gives me an idea that I can therefore use a one dimensional equation in order to solve it. That makes my mathematical derivation relatively easier to handle. That's the reason we take gradual channel approximation. But if my channel lengths are reduced drastically, they are reduced drastically, then the GCA or the gradual channel approximation does not hold good, right? Let's come to the charge sheet model. What is the charge sheet model? Charge sheet model assumes that the inversion layer is basically a sheet of charge, right? So if you remember my previous classes, you will understand that in this channel is basically a very thin channel which you see from the source to drain, right? It's almost a sheet of charge which you see, and that's the reason it is known as charge sheet model. So these two assumptions are sort of a valid assumptions for long channel devices and for biases which are governing the long channel devices. Let me come to the derivation of the gradual channel approximation. Now, the following assumptions, we are assuming that the source is grounded. So, you see the source is grounded here, and the bulk or the body is also grounded. So, your p type substrate is grounded, and your source, which is highly doped n plus region, is also grounded. I apply bias where I apply bias to the gate side with respect to the source. So, when I say VGS, it is basically VG minus VS, but since Vs equals to 0, therefore, it is the absolute value of the gate voltage which I apply. Similarly, I apply a drain voltage with respect to source again, and therefore, write down is to be as VDS, correct. So, I have a VDS on the drain side, and I have a VGS on the gate side, and I am assuming that the gate voltage is greater than the threshold voltage of the device. So, I have assumed that my VGS is greater than threshold voltage of the device. Now, if you look very carefully, what is the reason why I have drawn this is that let me rub this portion and I will show you what the idea here is. Now, let's come back to this diagram here, and you will see that since you have applied a gate bias, right, and therefore a channel is formed. Suppose you didn't have applied any drain bias, the thickness of the channel, right, if I assume there is 2, the thickness of the channel will be same, thickness will be same throughout the length of the device, right. Why? Because the electric field is exactly the same both on the source side as well as on the drain side, and therefore the thickness of the electron which is being generated here, which is the inversion layer, will be there. However, if I now start to increase the drain to source voltage, then what happens is, because of an enhancement in the VDS, the depletion region on the drain side starts to become larger and larger. Why? Because you are basically reverse biasing drain with respect to body. Body is grounded, p type, n plus region is drain, and you are giving a positive bias to the drain. So, basically reverse biasing the drain to body. As a result, the depletion region thickness will be larger. When it becomes larger, it starts to eat away into the channel, and therefore, you see as you move from source to drain, the channel actually starts to taper out, right. It starts to taper out, which means the thickness of the channel actually starts to reduce as you move from source to the drain. We define the channel potential with respect to source as Vc with respect to Y. So, Vc is channel potential, and this is Y dependent. Y dependent means it is depending on the value of at which place you are measuring the value of the channel potential. Okay. Also, we have told you that VGS is greater than VT, and therefore, inversion channel is formed. Now, let us assume this thing that we assume that the threshold voltage is constant, and we try to find out the total charge between Y equals to 0, this point, and Y equals to L, this point. So, this is my 0 0 point, and this is 0 L point. So, this is 0 0 and this is 0 L, right, and this is the x direction which you see on the transverse direction. With this basic assumptions available to you, let's come to the concept here. As I told you that here that we have, therefore, Vc equals to 0, right. The assumption which we follow is that at Y equals to 0, my source voltage is 0 and my channel potential equals to VDS. Now, so you see here, therefore, that the potential which you find out, right, the potential which you find out here in this case is that you will have Vs equals to 0 and Vds equals to Vc value at y equals to L. Now it is assumed that the whole of the channel is inverted, therefore my gate to source voltage should be greater than Vt0, where Vt0 is basically the threshold voltage of the device, right. Now that is the reason I have written Vgs should be greater than Vt0, right. And gate to drain voltage Vgd, which is nothing but Vgs minus Vds, right, that should also be greater than equals to threshold voltage. I will try to explain to you why do I write that. So if you write Vgd, it is nothing but Vg minus Vd, right. Vg is nothing but Vgs and Vd is also Vds because source is grounded, correct. Now you see, quite interestingly, if Vgs equals to Vds, right, if they are exactly equal to each other, then there will be no electric field happening in this region, and effectively your no channel formation will take place. So I need to assume that the difference between these two should at least exceed the threshold voltage of the device, then only I will be 100% sure that the channel will be formed even at the drain end of the device itself, right. And that is very, very important observation which you should keep in mind. Now let us assume that the total mobile charge which you see in the surface inversion layer is given by this formula. So you see it is V. So what I am trying to find out is this is my sort of surface inversion layer. So this is the source end and this is the drain end, right. And as you move from source to drain, as you can see, it is basically tapering out, right, and that is what is happening actually. This is the channel width which you see, which I was talking, the third dimension, and I assume that I try to find out within a region dy how much amount of mobile charge per unit area is there, right, and that can be expressed as a function of the gate to source voltage. So if you apply a gate to source voltage which is Vgs, then out of Vgs, Vt0, which is the threshold voltage, will actually go to form the inversion layer, and therefore you need to subtract Vt0 from Vgs. This Vgs minus Vt0 is also referred to as a effective gate voltage, and sometimes in many of the literature you will see this to be as Vgs prime. If you subtract that from the channel potential, you get the exact value of the potential at that particular point. Now you know that Q is equals to C into V. So C is already Cox, the oxide capacitance which is available to me, that you need to multiply with the voltage which is available at that particular point Y, right. Now let us consider the incremental resistance in the differential channel. So resistance is basically, if you look, so dr will be, so for this dy incremental distance, my dr will be given by dy divided by w times mu n times qiy. What is w? Width. Mu is the mobility of the charge carriers, surface electron mobility of the charge carriers, and it also depends upon the inversion layer. So higher is the inversion charge density, lower will be the resistance, makes sense. Higher the mobility, lesser will be the resistance, larger will be the width, larger will be the number of charge carriers, and therefore lower the resistance. Higher the value of dy, larger will be dy, because the length increases and you very well know r is equals to rho L by A. From there you can find the value of this dy. So I have given you a basic formula, incremental formula here, which gives me a basic idea about the value of dr here. Now if you took dr, then I know that if you apply Ohm's law, and assuming Ohm's law is valid obviously in this region, we say dVc equals to id into dr. id is the drain current, and dr we have already found out by the previous case, dy by w. So I put minus times. Why minus? Because you are working with a negative charge here, right. Now since this equation therefore needs to be integrated from y equals to 0 to y equals to L. So when you integrate, so what you do is, so what you try to do is, you take id into dy on the one side, id dy on the one side, and the other all factors, this you shift it to the left side, on this side, cross multiply. However, width and for all practical purposes mobility is held to be constant, and therefore what you get, you are basically integrating the y from 0 to L and the channel potential from 0 to Vds, because Vds is the drain to source potential on the drain side, right, and that is known as drain to source potential which you get on the drain side, Vds. This gives you approximately equation. If you solve this equation, then you will be able to achieve the value of the current. Now let us look at the left hand side. On the left hand side, since let us suppose ID is constant, obviously ID is constant because your continuity has to be maintained, I get this L y dy. So it is basically dy, and this will be nothing but ID into L. That is what you get on the right, because if you integrate dy from 0 to L, we will get ID into L, and that's, if you look at the right hand side, you will get W into mu n, W into mu n. You will have a Cox coming into picture because you can replace this Qi, you want to replace this Qi by this expression. Once you do that, I end up having this equation, and you can now take L in the denominator, right, and you can take L in the denominator, and I get W into mu n into Cox. Please understand, now I have removed the sign current, minus sign, and I am assuming the absolute value of current to be true, right. One more thing which I should point out at this stage is I am considering that the mobility is constant, right. In reality, again, when you are using a very small channel devices or short channel devices, this is not true, and therefore you get W into mu n into C oxide is 0 to VDS VGS minus VC minus VT0 dVc, right, where VT0 is threshold voltage. Again, threshold voltage is considered to be constant. These two quantities are considered to be constant. Now once it is done, then if you integrate it, I get this expression here, right. ID equals to mu n Cox by 2 into W by L into 2 times VGS minus VT0 into VDS minus VDS square. If you look very carefully at this expression here, then you will see that the drain current, right, which you see on the left hand side, depends upon obviously depends upon the value of VDS, right. It also depends upon the value of VGS. All other parameters are in a sense fixed, right. This W by L is referred to as aspect ratio, and we have mu n C oxide by 2 into W by L into 2 times VGS minus VT0 into VDS minus VDS square. And this quantity VGS minus VT0, right, this is referred to as effective gate voltage. Effective gate voltage primarily means the amount of voltage which you have to give effectively appearing to the channel. So if you give a voltage of 2 volts and a threshold voltage is 0.5, then you basically subtract 0.5 from 2 to get 1.5, and 1.5 is your effective gate voltage which you see, right. So this is the actual voltage seen by the charge carriers in the channel. With this into consideration, we can look into the fact another way of writing the whole expression is that we define this to be as K prime, right. Kn prime we generally write down. If it is n type, we write this to be as Kn prime. So Kn prime by 2 into W by L into this quantity, right. Now Kn prime is also referred to as a process transconductance parameter, right, and Kn prime into Cox into W by L is also referred to as a conductance parameter. And these are all these are bias independent parameters. They depend upon the structure of the device and the material of the device, right. So how much is your Tox, how much is your W by L, how much is which type of carriers you are choosing, that will depend on define the value of Kn prime. Now this Kn prime into W by L divided by into W by L, this quantity, if you look, is referred to as K, conductance parameter, and by 2 into this whole quantity which you see in front of you. So this is my final expression where Kn prime is mu n C oxide and K equals to Kn prime into W by L. These two parameters you should keep in mind and will be useful for subsequent studies. Now quite an interesting way of looking at it is that this equation is actually not valid beyond the linear region or beyond the linear region, where VDS is greater than equals to VGS minus VT0. So VDS greater than equals to VGS minus VT0. This region is defined to as saturation region. Any applied drain bias less than this value will be referred to as a linear region. I have discussed this in yesterday's class also, but just to reassert the whole thing, that any voltage applied bias, drain to source bias, greater than VGS minus VT 0 will allow you to have a saturation voltage, or the saturation region. So this equation is valid in the linear region of operation, linear and non-linear region of operation, in a sense, right. I will show you how is it valid, and I can explain to you also. Let's look at this expression here, right. If you look at this expression, when VDS is very small quantity, let us say 0.01 or 0.05 or something, this quantity actually vanishes, because the square of a small quantity will be still smaller, right, and therefore this quantity actually vanishes, and what you are left with is ID times, right, k by 2 times 2 times VGS minus VT 0 into VDS, which means that the current is a linear function of the drain to source voltage. So therefore, if you start plotting the current, let me see if I have the current, let me have a look at it. Yes. So if you look at, this is what I was talking about, you see, it is almost a linear increase in the current which you see here. The current is actually increasing linearly with the applied drain to source voltage, right, and that is what it is reason, that is the reason you will always have this to be as a linear flow, and therefore if you plot ID versus VDS, right, for a fixed VGS, it will be something like this. It will be something not even non-linear, it will be almost like a linear flow will be there. As you start increasing the value of VDS, this parabolic terms comes to shoot in, and with the negative sign. So what you will see that this starts to taper out like this, right, it starts to lower, and lowering effect is because of this negative VDS value, which was not very was not showing its problem when your VDS was very small, because that quantity can be neglected. So at small VDS, right, VDS square can be actually neglected, but that is not true when your VDS is relatively high. When the VDS is relatively high, then this negative square term will be more effective, and as a result what will happen, ID which was supposed to go on increasing will now tend to taper out. So you will actually see that if you did not do any minus VDS square, you will actually see this going straight, but now the tapering action takes place, and that is the reason. So this is basically the nonlinear region of operation, this is the nonlinear region, correct. So I defined to you a nonlinear region, I have defined to you the linear region of operation. So Ohm's law will be valid at this particular point, right, and this is for a fixed VGS. Now intuitively you can think, and even from the equation you can understand that if the VGS value increases, if it becomes more, then you end up having a larger current for the same amount of drain to source voltage. So this is what you get. So if you see, for the same amount of VDS, you see your currents are much larger when your VGS value is larger. So if this is VGS2 and this is VGS1, and VGS2 is greater than VGS1, then automatically you see the current is also larger. Current larger means resistance is smaller, which means that I can use this also as a voltage variable resistor, VVR. It is referred to as a VVR, but JFETs are generally used, but I can use MOSFET by changing the value of the gate voltage. So gate voltage is a knob with me by which I can change the current, and the drain voltage of course is another one which we can do it. Now let us look at what happens if we enter into the saturation region. Saturation means where VDS is greater than VGS minus VTH. Now if you take VDS equals to VDSat, VDSat is nothing but the value of the voltage where VGS equals to VT0, then if you do a small amount of manipulation and you put this value in place of VDS, so I get this is VDS and this is VDS square, right, I get this into consideration. So you see it is 2 times VGS minus VT0 whole square, so 2 times VGS minus VT0 whole square minus once VGS minus VT0 whole square. So one, if you subtract, you get this. This is quite interesting now. If you look at the drain current now becomes only a function of the gate voltage, and it does not depend upon the drain voltage, right, and beyond the saturation. Before the saturation it was always depending on the on the gate as well as on the drain voltage. Beyond saturation for ideal MOSFET, it does not depend upon the drain voltage, right, and that is quite a interesting phenomena from device point of view. This, if you look at this right hand side figure here, then this is the region which you see, the dotted curve is the region where I show you VD sat. These are the points of VD sat, which is equals to VGS minus VT0. So, as the VGS value goes on increasing from VGS 1, 2, 3, 4, this value tends to increase, and therefore, you see this point actually shifts to the right. It was initially here, then it becomes here, and then finally it becomes somewhere here in terms of VDS. Why? Because as the VGS increases, it increases, and it is a parabolic increase which you see. So, we define, therefore, let me rub this portion here. So, the red region which you have shown is the ohmic region. Why? Because here the Ohm's law is actually being followed, right. Why? Because it is almost a linear region. You see, there is a small nonlinear region here. This small nonlinear region, if you make a star here, then the small nonlinear region actually falls, sorry, this is the reason why we get a small nonlinear region, because of this factor, correct. So, I get this linear, and then but interestingly, though I have not drawn it here properly in that sense, but if I draw it properly and show it to you for various values of VGS, I will see that I will have something this, then I have this, then I have this, and then I have this. As you can see, as the gate voltage goes on increasing, the current is increasing, but for the saturation region, which is the right hand side, it is almost independent of the drain voltage, it is almost constant. So, this is the place where it behaves as a ideal current source with impedance very high. But on the left hand side is the ohmic region, which depends on the value of the gate voltage. Higher the value of the gate voltage, lower is the resistance, higher is the conductance, right. So, this way MOSFETs can be used as a voltage variable resistor, but MOSFET can also be used as a switch. How? You just see. If you take your VGS exactly equals to VT0, then if you go back to this equation of the saturation, so let me either this or you can take this, when VDS is very small, this vanishes, and when VGS equals to VT0, this function vanishes. For what? For VGS 0 equals to VGS equals to VT0. When this vanishes, ID is approximately equals to 0, right. This region is defined as the cutoff region. So, what is a cutoff region? Cutoff region is a region where the current is 0. Ohmic region is the region, or linear region is the region where Ohm's law is being followed. I have a nonlinear region also in the middle, where the current is a nonlinear function of VDS, and I have a region which is independent of VDS depending only on the VGS, that is the saturation region. So, if you bias your device here, it will be saturation acting as a current source. If you suddenly bring it down here, you are cutting off the device from on state to off state. So, this is on state, this is off state. So, here you can use it as a switch in all practical sense, correct. So, let us quickly go through this concept of inversion in 3 parts. The inversion in the first part is weak inversion, when your psi s is between phi f and 2 phi f, we have already defined earlier. We have a moderate inversion when psi s equals to 2 phi f, and we have strong inversion when you have psi s is slightly larger than the 2 phi f value, right. So, weak inversion is between psi s and 2 phi f. 2 phi f is the point when psi s becomes equals to 2 phi, psi s is basically the potential at surface potential, right, the surface potential, and phi f we have already defined kT by q ln Na by Ni, right. Now, when psi s equals to 2 phi f, it becomes as much n type as it was initially p type if you are taking an n channel enhancement mode MOSFET, and anything larger than that voltage if you give, you will see a strong inversion layer being formed. Now, typically delta phi, for all practical purposes, we consider this to be as a 6 phi t, where phi t is basically kT by q at 300 Kelvin. At 300 Kelvin, this is approximately equals to 25 millivolts. So, 6 phi t means if you multiply this with 6, I will get 150 millivolts. So, any surface potential which is 150 millivolts greater than 2 phi f will always entail approximately a very large or a very strong inversion. Very strong inversion primarily means that inversion layer where large number of charge carriers are already present, right. Let us finish this talk by looking at the transfer characteristics. This is the transfer characteristics, where we are plotting the drain current versus the gate voltage. And you see, when the gate voltage is equal to threshold voltage, the anything below this, the current is, there is no current, and you can understand why. Because there is no inversion charge being formed or inversion layer being formed. When there is no inversion layer, there is no question of any current being formed, and that is the reason there is zero current beyond Vt, and anything above Vt you see a sort of a parabolic increase in the current here, right, or a large increase in the current which you see in this case. And why is it so? Because you see it is square of Vgs, right, mu n C oxide by 2 W by L Vgs minus Vt0 square. So square basically therefore means that I will get a parabolic function in this manner, and that is what I am getting in the transfer characteristics of the device. You see, the transfer characteristics of the device is a parabolic function which you see here, correct. Now the obvious question asked is why we are studying this. The motivation for studying this is that you should know a priori how much current the MOSFET is carrying in saturation, in linear and nonlinear region, and how can I make the device go from on state to off state, right. These 2 or 3 takeaways are important in this class, right. And the last part of the talk is basically to do with the one basic idea, that let us look at the impedance at this point. You see, it is almost a straight line. I have already discussed with you, del id, if you find out del v divided by del I, then basically del I is 0, and therefore del v del I will be equals to infinity, and that is what you will get. An ideal therefore a MOS capacitor. So if you take a MOSFET, right, an ideal MOSFET, right, in saturation will behave as a current source with resistance R out to be equals to infinity, right. Infinitely large resistance will be there for the case of a MOSFET. So let me recapitulate what we did today. We studied basically the MOSFET, its IV characteristics, various regions of IV characteristics, and how they are dependent on the value of the voltages available to you. And finally we ended up the concept of definition of inversion in 3 parts: weak, moderate and strong inversion. And then we also understood what will be the resistance of a current source, and how I can therefore switch on and off a MOS device. With this, let me end the talk. Thank you.